We had just solved the wave equation in the previous recording. Here is the problem, the whole problem. It is a partial differential equation, boundary value problem. That's what we're doing now. Here's the partial differential equation itself. These boundary conditions are that this vibrating string is held at a height of 0 at each end. And then these conditions are the initial conditions. There's an initial displacement of the string, and there's initial vertical velocity of the string. And we solved that these were just general functions. And here was the solution. Here it is with just in general the A's and B's. And here's the formulas for the A's, B's, with those general functions in them, the f of x here and the g of x here. Now, the kind of problem you might run into if you're taking this in college or something, is that the whole problem is the same problem. Whoops. Same boundary conditions, but you actually have specific initial conditions. So not just a general f of x and general g of x, but actual functions. In this case, f of x was 0, initial displacement, so it wasn't initially displaced at all, but it did have an initial velocity of this function here. Well, I don't really like this example because we're not really solving a partial differential equation boundary value problem. That's already been solved. All we have to do to complete the solution is take these integrals to find the A's and the B's. So this problem is just kind of one long take an integral problem. But if you don't care about that, you could skip this recording, but I'll keep going through it because some people are rusty on such things. And I try not to use, what is it? Wolfram Alpha if I don't have to. So anyway, we had the general solution. Since the f of x's are 0, all the a sub n's are 0, so that's good. So all we have to calculate are the b sub n's. This problem now is just solve that integral, one integral. So there's what that integral is. There's a formula from the b sub n's. We have a g of x, it's this, so we'll put that in our integral. So now we're just left with evaluate that integral. The way I do it, I'm still going to use a table. I'm not going to totally do it from scratch. I'm going to use a table, and I'll skip ahead. These three things here, that's what I have in my table. You might have your own table of integrals. If you really want to cheat, use Wolfram Alpha. I don't have this explicitly in my table, this u squared, but I have u to the n, so I can use that formula along with these formulas. So now I have a formula for this thing, u squared sine. Anyway, that's what I have from the tables. Well, first thing I'll do here is I'll split this up into 2. I'll have an xl times this sine stuff. Bring the L out here now. Then minus an x squared times the sine. And to use the table, you'll notice they all have something like a u, sine or cosine u, du. So I need everything I'm going to call u. So I'll call arguments of the sine u. So I need to multiply this x by, let's see, n pi over L. And this dx by n pi over L. Where I have a u there and a du back here. Everything's in terms of a u. And since I multiplied by that twice, I have to multiply by its inverse twice. That's where I get this L over N pi squared. Similarly with this guy, the x squared, I'm going to have to multiply by N pi over L squared. And look at the N pi over L dx here. And so I had a total of power of 3, so I need to multiply by its inverse. These guys are now in the form of what's in the table. So now we're just using the table. So it's, let's see, it's the first guy, which is this guy, minus all this, and this is the u squared, so this thing. I evaluated all between the limits 0 to L. I'm not going to go through all that arithmetic. Let's see, one thing, cosine of N pi is minus 1 to the N. That's something we're going to use. So we don't like to leave cosine N pi in there. Switch it to, well, after some algebra and simplification, you get it down to this. But all these cosine N pi's, let's see, these two guys cancel. So we're just left with this. The cosine of N pi is minus 1. So all that mess kind of simplifies down to this. So here's our solution, because all the A's were 0, and here's what the B sub N's are. Put it all together, it would look like this. And we could pull out anything that doesn't involve N, we could pull it out up front if we want. Don't pull out anything that involves N, because that's part of the sum. You got to leave all N stuff inside the sum. Pull out the 4L cubed over pi to the 4th A. Anyway, here's the solution for that problem. Like I said, that was really a tedious exercise in evaluating integrals. You didn't really solve a partial differential equation.